Good morning. For today's lesson, also posted a little late, I apologize for that. But for today's lesson, we are going to learn how to graph polar equations. So, yesterday we learned how to graph polar coordinates, and now we're going to apply that knowledge to graph polar equations. So let me give you a few examples of what these equations could look like. It might look like r equals 2, or you might see something like theta equals pi over 4. Or you could see something like r squared equals 9 cosine 2 theta. Or r equals 5 times 1 minus sine theta. I'm trying to see if I see anything else. R times theta equals 3. Here's another one. R equals 2 cosine of 2 theta plus pi over 3. Okay? So these are all kinds of examples of polar equations. And so I want to graph them, and then I will talk about some of the interesting aspects of these and some things you can watch out for. And you can pay attention in the learn part of your lesson to these particular highlights. Okay? So let's go to the next page and let's graph a couple. So the first thing I want to do is I want to graph r equals 2. All right? And so I'm setting this up. So we have some polar graphs we can use. And I want to do r equals 2. So there's my first equation that I want to graph. So I am going to make a table for this, just like I would with regular coordinates, except it's r theta. Now, in this case, r is equal to 2. So no matter what I put in for theta, r is 2. If theta is 0, pi over 6, pi over 4, pi over 3, pi over 2, etc. No matter what angle I have, I always have 2. And so let's go through this really quickly on the graph. So on our graph down below, we have r equals 0, which is here, but we plot the radius 2. And then at r equals pi over 6, we plot 2. At r equals pi over 4, which is halfway between pi over 6 and pi over 3, we plot 2. At r equals pi over 3, we plot 2. At r equals pi over 2, we plot 2. Do you kind of see what's happening here? What kind of graph are we going to end up with if we plot 2 no matter what angle we have? And so this becomes the way to graph a circle. Now, just remember r equals 2, and in our rectangular coordinates, we have x squared plus y squared equals 4 to graph this. Now, which equation is more complicated? The rectangular coordinates or the r equals 2? And it should be obvious that the rectangular coordinates are more complicated than the polar coordinates. So what that means is likely there are some things that are harder in polar coordinates than rectangular, and some things that are harder in rectangular than polar. And circles are one of those things that are super easy in polar coordinates. You're basically saying, graph me the object that has a radius of 2. Well, that's a circle. So that makes a lot of sense. All right, let's do the second one. So the second graph I wanted to do was theta equals pi over 4. Okay, so theta equals pi over 4. So in the same way, I want to make an r theta table. Now, just like on the circle we just graphed, theta never changes. It's always the same no matter what radius I pick. So if my radius is 1, -1, 2, -2, no matter what my radius is, my angle is always pi over 4. Okay? So, pi over 4, if you'll remember, is halfway between pi over 3 and pi over 6. All right? And so we can graph any radius on that. 1, 2, that's the radius of 1, the radius of 2. There's the radius of -1 and -2. And we could have had 4 pi over 4 like this. What are we going to get in this case? We're going to get a line through the origin that goes on the terminal side of the angle. It's right on that terminal side. So pretty slick, right? So this is how you graph a line in polar coordinates, or at least some lines. This lines through the origin are easy because we just have to specify the angle. Okay? And the particular line we graphed was y equals x, and you can see how that compares to theta equals pi over 4. Both of those are pretty snappy, fairly straightforward. Wow, had a big yawn there, I apologize. Let's go on to a few more graphs that are a little more complicated than these two. Sorry, I was muted there for a minute. I want to go ahead and let's graph this one. Now, again, I'm going to make a table of values to help me out here. Okay, r theta. Now, notice this is not like the last ones. I'm going to pick a theta value, and that'll give me an r value. So, for instance, I'm going to pick, and since this is 2 theta for the angle in here, if I double the angle, then it'll end up telling me when I take the sine. So I want to take the sine as special angles, then I can just use the table. So what I'm going to do is I'm going to let theta be 15 degrees or pi over 12. Either one, you can think of it as either way. And then I want to go to 22.5 degrees. All right, which I believe that might be pi over 10, but we can calculate it later. Then I want to go to 30 degrees. I also, gosh, I want a 0. I want to start at 0. And then once I get 30, then I want to go to 45 degrees, okay? And let's just do these first. Now we'll do the 0 first. I forgot to put that, so I apologize. So we plug in 0 for theta, so I get the sine of 0. The sine of 0 is 0, and so 0 times 2 is 0. So 0, 0 is a point on our graph, okay? And that would be this point right here, okay? Then I go to 15 degrees, which is pi over 12, all right? And I'll show you why I chose 15 degrees. Because 2 times 15 is 30 degrees, or 2 times pi over 12 is pi over 6. And the sine of pi over 6 is 1/2. 1/2 times 2 is 1. So I can go on the 15 degree, which I plugged in, and I can go out 1. So I go right there, okay? Now I go to the 22.5 degrees. Why did I pick that? Well, because 2 times 22.5 is 45. So the sine of 45 degrees, or the sine of pi over 4, 22.5 is pi over 8. So 2 times that is pi over 4. So that gives me square root of 2 over 2 times 2, which will give me just the square root of 2. So 22.5 degrees is halfway between 15 and 30, and I go out square root of 2, which is approximately 1.41, okay? And so that's about there. And then I do pi over 6, or 30. So 2 times that is 60, or pi over 3. Sine of pi over 3 is the square root of 3 over 2. Times 2 gives me just the square root of 3, which is about 1.8. So on the 30 degree mark, we go out to about 1.8, okay? Now, if you start to connect this, you start to see that you're getting a little bit of a shape. Now, 45, if we plug in pi over 4, we get 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1. 1 times 2 is 2. So we get 2. And so on the 45 degrees, we get 2. So what we see is we're starting to get a little loop here. All right. Sorry. Okay, I'm back. Had to plug in my iPad. It's about ready to run out of juice. So, as you can see, we're now following through. And you see what I do by keeping track? I'm drawing this as I go. Now we would go ahead. Now we would go the next 45 degrees, right? So 45 gave us this, and now we would go to 60 degrees, which is pi over 3, okay? And then we would go to 67.5 degrees, which is probably to 3 pi over 8. All right. And then we would go to 75 degrees, all right, which is 5 pi over 12. And then we would go. Now, I've done this before, so I'm kind of thinking through these degrees to make sure I get a good picture, okay? And then we could go to 90 degrees, all right, which is pi over 2. In any case, we'll plug these in now. If you plug in pi over 3, you get 2 pi over 3. Sine of 2 pi over 3 is still square root of 3 over 2, so you get the square root of 3, all right? And then you plug in 67.5 degrees, or 3 pi over 8, you get 6 pi over 8, which is 3 pi over 4. The sine of that is square root of 2 over 2, and that would then give you the square root of 2. So notice the numbers are repeating, but in reverse. We went 0, 1, square root of 2, square root of 3, 2, and now we're going 2, square root of 3, square root of 2. This one should be 1, and this one should be 0. So let's check. 5 pi over 12 times 2 is 10 pi over 12, or 5 pi over 6. Sine of 5 pi over 6 is equal to 1/2. 1/2 times 2 is 1. Plug in the pi over 2 and you get the sine of pi, which is equal to 0. And 2 times 0 is 0. So yes, we did get them in reverse. And so if we mark them at 60 degrees, we're going to be about 1.8. At 67.5 degrees, we're going to be at about 1.4. At 75 degrees, we're going to be at 1. And then at 90 degrees, we're going to be at 0. So it looks like this will loop around and take us right back to the origin. Okay? Now, I want to shrink this just a little. And can I grab the graph? No. I want to shrink it just a little because I got to continue the table, r theta. And so if you want to graph this again, now you want to go to you've now done a whole first quadrant. Okay? We've gone from 0 all the way to 90 degrees. Now we're going to mimic that in the second quadrant. Okay? So now we're going from 90. So just think of each of these degree things as just added on to 90. All right? So 90 plus 15 is 105. 90 plus 22.5 is 112.5. 90 plus 30 is 120. All right? So we're putting degrees here. Could do radians, so you could add pi over 2 to all the radian values. It doesn't really matter which one. You just want to keep track as you go. And then I'm going to add 90 plus 45 is 135 degrees. Now, what would I expect to happen? Because the 105 has the same reference angle as the 15 degrees, I would expect to get the same values. So I would expect to get 1 square root of 2, square root of 3, 2 out of these in the same order. Okay? However, when I put 105 degrees into here, I get 2 times theta, which is 210. That's a third quadrant angle. The sine of 210 is like the sine of 30 degrees, except it's in the third quadrant, so it's going to be negative. So I'm going to have negative 1/2 times 2, which is negative 1. And that's what happens to each of these. And so I come back, and when I do 105 degrees, oh, my finger touched something. Sorry about that. And when I do 105 degrees, which is right here, okay, I need to go negative 1. So 105 is up that way, but negative 1 is this way. Okay? And then I go to 112.5 degrees, and that's halfway between 105 and 120. And then I'm going to go negative square root of 2. So halfway between there is 1.4. Okay? Then I go to the 120 degrees, and it's negative square root of 3. So here's 120, but I go in the negative direction. So I put that 1.8 out there. And then I do 135, which is right here. But 135, I got to go the opposite direction, so I go to negative 2. All right? So notice how this swings around like that. Starting to see how this works. So now, then basically we want to add these angles onto 90. So then I do 150 degrees, 157.5 degrees, 165 degrees, and 180 degrees. And we can do the 180 really quick. 2 times 180 is 360, or 2 pi. So the sine of 2 pi is 0, so we're going to get 0 here, right? Pretty slick what's happening. And you can see that we're probably going to get these same numbers in reverse. But if I plug the 150 in, 150, if you want to know, is 5 pi over 6. So 2 times that becomes 10 pi over 6, or 5 pi over 3. And the sine of 5 pi over 3 is negative square root of 3 over 2. So this becomes negative when you multiply it by 2. These will also be negative. So I'm doing this all by hand. So now I go to the 150, but I only go out to the square root to 1.8. Then I go to the 157.5, and I go to the 1.4. Then I go to the 165, and I only go out to negative 1. And then I go to the 180, and I'm at 0 again. And you can see that our graph has done this so far. Now, if you were to continue this and go all the way around to 2 pi, which you should do every time, you would get the other 2 leaves of this rose. All right? And the other 2, so you would come around like this. You would come around like that, continuing it, and then you'd come around like that and continue. All right? Now, when I did these, I would make the whole complete table so I could do this. Now, you have to remember, that's in the days before a graphing calculator or Desmos. So let's go to Desmos and do this. We've never done these on Desmos, so we probably should, right? So let's go to the graphing calculator for Desmos, and we want to do this problem. So we need to go to our tool, and let's see. Oh, I don't see anything there. So now that means I'm going to look up a question here. And I'm going to look up, how can I do polar coordinates? So let's go to the user guide, and I start scrolling through the user guide. And they tell me about sliders. Oh, it won't slide anymore. I'm not able to do this very well on the iPad. So give me just a second. Okay, so here's what I did. Sorry, I had to dink with this a little bit because it's on my iPad and it's inside a program. I got to keep it working on the web. So basically, I want to type R equals 2 sine 2 theta, which is our equation. So I go to the ABC and I can type R, then go back, equals 2 function sine 2, and then I go back to the ABC, and you'll look over here underneath the P, where we normally have the colon and the semicolon, they give us theta. And when I type that, you will see that my theta becomes exactly the graph that you and I wanted. All right? Okay? And that's what you and that's exactly the graph we got. I apologize. I'm sorry. I was trying to say that, and I didn't say it very well. I got distracted by something. But you can see that's the graph that we got. And so you can do these graphs on Desmos, but you really ought to try them by hand at least part of the way and then check with Desmos just so you get a feel. Now, I would generally almost always do polar coordinate graphs using check technology. But to understand how to graph them out, I need to do it by hand. So don't get lazy and just use the technology. Try to do a portion of it and then go do the rest. Now, this is how you would do every polar coordinate graph. They're all done the same for the most part. I'll show you a couple of other interesting ones, but that'll be what we do in just a moment. Okay? So anyway, I hope this helps to recognize Desmos can help you draw these. These are challenging to draw, but you can come up with a very good sketch that matches what you can get from technology. Okay? Let's look at one more. And so here I go again. R squared equals sine theta. Now this is different because it has an R squared. So again, I pick a theta. Now, I just have sine theta, okay? So I'm going to pick my standard angles, 0, 30 degrees, or pi over 6, 45 degrees, or pi over 4, 60 degrees, or pi over 3, 90 degrees, or pi over 2. All right? And I plug in 0. Sine of 0 is 0. So r squared equals 0, which means r equals 0. Okay? So again, we get 0, 0. All right? And then we go to the next one, pi over 6. So the sine of pi over 6 is 1/2. So we have r squared equals 1/2. So r equals the square root of 1/2, which is 1 over the square root of 2, or it's square root of 2 over 2. In either case, that's about 1.4. So on 30 degrees, we go out 1.4. Okay? I just thought of another way to do this. Let's do this. Let's put a red one there. And this is 1 over square root of 2. So that's red. That'll show us. So now let's go to blue. So I put pi over 4. Sine of pi over 4 is square root of 2 over 2. So this is r squared equals square root of 2 over 2. So then you take the square root. So it's the square root of the square root of 2 over the square root of 2. That's ugly. That's terribly ugly. So I have to go to my calculator just to figure out as a decimal what that is. And that's kind of the issue with some of these. Okay? So square root of 2, square root of the square root of 2, and then you divide that by the square root of 2. All right? And I ended up getting 0.84. All right? And so if I plotted that point on the pi over 4, I would go about 0.85. I would put it there, okay? And then we go pi over 3, which is square root of 3 over 2. So on that one, we get r squared equals square root of 3 over 2, which means r is the square root of the square root of 3 over 2, right? Or the square root of the square root of 3 over the square root of 2. Either way, so I have to calculate that on my calculator, which I can do by just substituting the right numbers, and I do that, and I get 0.93. So this one's about 0.93, and so now at the 60 degrees, it skips back up. So I'm not sure what we have. I might need to do a 15 degrees just to figure it out. So I want to take the square root of the sine of 15 degrees, and that's 0.50. Okay? So that's 1/2 approximately, so right here. So it looks like, or on 15 degrees right there. So it looks like we come up, and then we come down, and then it looks like we might be coming up again. So I'm not quite sure. This one would be really challenging to graph doing this way. And so I would definitely want to use Desmos on this particular one, okay? And so it's r squared sine theta. So let's try and do that. R squared equals function sine back theta. And now we've got everything we need. It does not like that one. Oh, it doesn't like the r squared. So that presents a conundrum on Desmos. Let me check my other calculator. I'll be right back. Okay. And so, looking at this Desmos graph, notice by entering r squared equals sine theta, Desmos did not like that. Why didn't it like it? Because Desmos always likes you to enter y equals, or r equals if you're doing polar coordinates. But if you do r squared, it's not going to like that. And it's so what I did is I ended up splitting it up, taking the square root of both sides, and then graphing the positive and negative square root. And it turns out that gives me two circles on top of each other, which creates a figure 8. So this graph right here is really the graph of a figure 8. Okay? And so somewhere on my calculations, I made a bit of a mistake. So it should be probably this red one. But if I look at this right here, or it could have been the blue one, because what could have happened when I did this, I'm looking, it might have come around like this on the graph, but this looks closer right here. So I feel like the red one is where I made the error, okay? Now, you'll notice that this, on the Desmos, it only goes up to 1. And so this one is definitely wrong. So I've made some mistake here. And not quite. Sine of pi over 6 is 1/2. And the square root of 1/2, oh, it's 0.7, not 1.4. So it would have been down there. So that was the mistake I made. So you got to really, it's 0.71. So you got to really make sure that your approximations are done correctly as well, or that leads you to the wrong spot. So now I can come in here. All right, and it looks like my graph is, oh, there we go. Now I got both layers done. So now I can come in here and I can do the right graph. So we went to 0.7, 0.8, and then I think close to 0.9. So we're coming around like this up to the 1, and then we're going to come back around down. Now, if you square up your screen, that looks like 2 circles on top of each other. All right. Okay. So now that we've found the error, and this is very typical in polar coordinates when you do them by hand, but I definitely want you to work through this so you get good at finding the points and approximating, putting it on the graph, and then check with Desmos. But I like doing Desmos. For polar coordinates, it can't be beat. It's so good at helping you and just gives you really nice pictures. So I would encourage you to do that. Okay? So let me see. What would be the other thing? There's one more thing I want to talk to you about this particular section. So for this section, the other thing that typically happens in the old days, because I didn't have Desmos or a graphing calculator that would do these easily, we would actually start to learn the shapes. So a cardioid is a particular shape, and it looks like a heart. They usually have this kind of a shape, all right? And they could be turned sideways or upside down, but they're cardioids, but they generally look like this. They have A times 1 plus or minus cosine theta equals R, or A times 1 plus or minus sine theta. And then the cosine ones are turned sideways, so they look like this. And the sine ones are upside down and right side up hearts. All right, those are called cardioids. So you know if you get an equation that looks like this, where A is a number and you have 1 plus or minus a sine or cosine of theta, you're going to get a cardioid. Now, if you have these kinds of equations, these are called roses, typically, and they look like this. R equals A cosine in theta, or R equals A sine in theta, where n is a positive integer. Okay? Now, if n equals 1, if n equals 1, you get a circle. All right? But if n equals 3, you get what's called a 3-leaf rose. So it'll look like this. Okay? And it could be rotated. If n is equal to 4, you get a 4-leaf rose, which is similar to what we got. Or excuse me, if n is equal to 2, you get a 4-leaf rose, which does basically this. Oops, I got this one's not down enough. There we go. So, and that's a 4-leaf rose if the n is a 2. And then you get, if you have an r squared, so r squared equals a squared cosine 2 theta, or it's equal to a squared sine 2 theta. If you have something like this is called a lemniscate. All right. And they basically are like 2-leaf roses. 2-leaf roses. So instead of a 3 or 4-leaf rose, they basically look like the infinity symbol, and it can be rotated. All right. So there are lots of other polar coordinate graphs that there are things called logarithmic spirals. One of my favorite names was called the Witch of Agnesi. It just means it's a hard graph. So you get all kinds of really great names for polar curves, okay? And I've always thought the names were really funny, but in general, we kind of stick with these basics and we learn how to draw them. But these others are actually really fun and different, and especially difficult if you do it by hand, but super easy if you know how to put them on a graphic calculator or like Desmos. Okay, that's all for this lesson. See y'all later.